So you have already seen that methods share some properties with operators. And two of the properties they also share are applicability and relevance, although they are defined different here. Applicability is actually very similar. So we say a method instance is applicable in a state S if all the positive preconditions of the method are satisfied in the state, so they must be elements in that state, and none of the negative preconditions must be in that state. So the intersection of the state and the negative preconditions must be empty. This is exactly the same way we've tested whether the preconditions of an action are satisfied in a state. But the definition of relevance is quite different from what we've seen previously. So we want to define when a method instance M is relevant for a task T. Since we don't have effects in methods and we don't have goals in planning problems, the definition of relevance must be quite different from what we've seen previously. And we define relevance here with respect to tasks that we want to accomplish. And a method is relevant for a task if there is a substitution sigma such that the task that we're trying to accomplish is the same as the task described in the method. Remember, the task of a method describes what we can accomplish with that method, and if we have a task T in a task network that we can make the same with a substitution sigma as the task of the method, then we can use this method to accomplish the task. And the method is relevant for the task. And if we have a task network that contains a task T, and we have a method that is relevant for this task under some substitution sigma, then we can apply this method by decomposing the task. So we define the decomposition of a task T by a relevant method M under substitution sigma. And we define it as follows. We define a decomposition function delta that takes exactly those three arguments, the task, the method, and the substitution, and it simply returns the instantiated network that is associated with the method. So every variable in this network is replaced according to the substitution, or if the task was totally ordered, then we can return the sequence of subtasks instantiated with the substitution sigma. That is what we call the decomposition, and delta is the decomposition function for a task given a method and a substitution. And here is another quick example to illustrate applicability and relevance in the Dogwalker robot domain. The world state that we have is the same state we've seen earlier. We have one crane and 3 piles, and there are 3 containers on the first pile. Now, suppose our task T is to move the stack P1 to Q. So we don't have a task that says we need to move it in an ordered way, we just have a task to move it at all. And we want to move it from P1 to some other unspecified stack because Q is a variable here. The state S is as shown here, so this is our initial world state in which we have this task to accomplish. Then we can look at the following method instance, mi, which is recursive move p1, p2, c1, c2. So remember, this is the pile from which we're moving, this is the pile to which we're moving, this is the container we're trying to move, and this is the container from which we're taking it. To check for applicability, we need to examine the preconditions of this method. And if you remember, there were 2 positive preconditions associated with this method, namely instantiated that the container C1 must be the top of the origin pile, and we can see in the state here C1 is the top of the origin pile, so that precondition is satisfied. And the other precondition was that the container C1 that we're moving is on top of C2, and again you can see C2 is the second container here, so the second precondition is also satisfied. There were no negative preconditions, so we don't need to worry about those, which means our method mi is applicable in the state shown here. And to test for relevance, we've got to see whether we can make the task accomplished by this method the same as the task that we are trying to accomplish. And indeed this is the case because the task symbol is already the same. It is move stack that is also accomplished by recursive move. And the 2 parameters of the method's tasks are p1 and p2. And P1 is also the first parameter of the task we're trying to accomplish. The second one is Q. So we can make these the same if we apply the substitution where we replace Q by P2. in which case the task would be move stack P1, P2, and it's the same for the task we're trying to accomplish and the task that is accomplished by the method. So the method is indeed relevant for this task under this substitution. This means you should now be familiar with the three new concepts that we've introduced for task network planning, namely tasks, task networks, and methods.